Welcome everyone for our heat pump technology webinar. My name's Jarrod Leak and I'm the CEO of the Australian Alliance for Energy Productivity, or A2EP. If I just start off with a couple of introductions who you can see up on the screen right now. I can see first Doyle Richardson there from the Alliance Group, the Group Engineering Manager. Welcome to Doyle. I can also see Cordin Arpagaus from NTB University in Switzerland. Welcome, Cordin. We've got Mike Henry on with us today. He's from the EECA in New Zealand. Mike, great to have you with us as well. And we've also got Brian Mills from the Alliance Group in New Zealand. And sitting with him, we've got Grant Dewson from Active Refrigeration as well. And finally, we have Tony Kimpton joining us, a doyen of the refrigeration industry. So that's our panel for you today. And with that, I shall, we'll have some introductions and further discussion from them later, but with that, we shall start the webinar. So I'll share my screen and away we go. And here we are. So again, welcome to this presentation on advances in industrial heat pumps. And I'd just like to start off this presentation by acknowledging the traditional owners of where I am living and broadcasting from today in the northern suburbs of Sydney, that being the Darramurrugal people, and I pay my respects to their elders past, present and emerging. And for those of you who don't know about A2EP, we are a non-for-profit organisation that is funded by our members. Let me just click up the members there for you. And we have our members here who share our mission to double Australia's energy productivity. In short, energy productivity is about getting more dollars from less megajoules. And at A2EP, we help drive transformational change to make this happen. We do this in several ways by coordinating government-sponsored programs that connect end users, researchers, consultants, and technology providers. We also prepare publications that help guide policy and investment decisions, as well as running webinars such as today. Importantly for A2EP, we're not just about roadmaps and reports, we're very much about making them into reality. And as we're doing right now with ARENA and the process heating studies that we're doing that is leading into new projects, and I'll tell you a little bit more about that one later. So today we're going to start with a summary of what's happening in this ARENA process heating studies, and then Dr Cordin is going to take us through the latest advances, what's happening in Europe, and we're going to learn a lot about the new technologies and new applications for heat pumps there. And then we'll have a panel discussion, and after that we're going to talk about local real-life experiences with heat pumps, and that's why we have people from the Alliance Group today. They've had their new heat pump installed since October last year, and so we look forward to hearing about some lessons learned and how that went. We've also got Mike Henry, as I mentioned before, from EECA in New Zealand. They've been overseeing many studies and implementations of heat pumps. So great to have Mike on board and tell us and share some more experience there as well. I mentioned Tony Kimpton before. He's going to join in for our panel and help us out with any discussions and questions you have regarding heat pumps and their application. Finally, and to end with today, I've got a quick summary of some of the grants and subsidies and programs that are available and ways to help you get started with using heat pumps. And then throughout today, I ask you to use the Q&A at the bottom of your screen. You can enter that your questions, and you can upvote those as well. So if you see a question that you like, upvote that, and that way we'll get to that question first. In your Zoom, an option in Zoom is to change your name. Feel free to change your name in Zoom so that we can see the organisation you're from and make sure it's clear who the question's from. So feel free to go ahead and do that. And just letting you know, this presentation will be recorded, and we'll be distributing that sometime next week. So without further ado, let's get into the material. I hope you sit back and relax with your afternoon cup of tea as we take you through what's happening with heat pumps. You've got the agenda there in front of you now, hopefully on your screen. So let's start working through that one. So heat pumps, those in Australia may well recognise this diagram at the moment, and this is from Dr. Alan Finkel, our Chief Scientist, his technology investment roadmap. And I draw your attention to the bottom, down the bottom corner there, where heat pumps are recognised as one of the larger bubbles and the larger opportunities to reduce emissions, and also one of the most profitable ones to change as well, showing that net cost of minus $150 to abate 1 tonne of CO2. So this is a huge opportunity, and certainly when it comes to process heat, some 8% of emissions in Australia. I think it's $8 billion a year spent on this energy, showing that there's an opportunity here, certainly, to change. Very quickly, I think most people here know heat pumps already, but just in case, heat pumps, think of it, a reverse cycle refrigerator. So this is taking a refrigerator, turning it on its head to create heat. People are probably aware of a domestic heat pump, and that's that little fella in the middle of the screen there. But what we're talking about today is industrial heat pumps. So not just sort of 3 kilowatts or 30 kilowatts, but up to 10,000 kilowatts and larger for a big industrial heat pump. That's what we're talking about today. Put this into context of where heat pumps can fit in terms of process heating and industry. If we take a look at the slide now, you've got the summary of heat pumps that, energy consumption in Australia. And if we assume that Tesla and EVs fix up transport and what have you, and renewable energy can fix up buildings, then there's a lot there of industry and process heating, which will not just be easily fixed up by solar and PV. This fuel for heating, some 52% there, about 900 or so petajoules per year of energy in Australia, a huge amount of energy there. And a large percentage of that is coming from natural gas and coal. And you'll see this is that 900 or so petajoules broken into how that temperature is created, not how it's used. And if we look at the down the bottom left there, that 150 degrees or so and below, that is the space that we're talking about there. Quite a significant chunk. And again, this is what's actually where the temperature is created, not where it's used. So it would actually, if we look at where the temperature is used, the heat is used, it would take up some of that 150 to 250 degrees part as well. But if we talk about that potential, that 9%, some 80 odd petajoules, we could be looking at an investment of $1 billion or so in heat pumps required if you wanted to displace just that 9%. And how have we come? How has A2EP come to be a part of heat pumps? Largely with coordinating a study funded by ARENA. ARENA sees changing from process heat to using renewable energy as a major long-term investment required. And A2EP has been running a program for them, which has seen us go through some 20 pre-feasibility studies and 10 feasibility studies, the majority of which have been assessing heat pumps and their application. We've seen some very good results coming from that one, and things like this now. We're starting to understand the sensitivity of the application of a heat pump in terms of the ROI, and we can see very clearly already anything below 65 degree temperature demand, you will get a coefficient of performance above 5 and a payback less than 3 years just on the energy savings alone. So huge potential here. Also, we see that if you utilise the cold generated from a heat pump, the COP potentially doubles, and again, great paybacks there. We also see that low utilisation for seasonal production being a major contributor to the return on investment for heat pumps. And you'll see that things like if you're drying fruit in a seasonal basis, that has a big impact. So there's a lot you need to do to optimise the design in that case. And also, and you see from the graph there, the cost of gas has a major impact as well. A few of the major success factors we're seeing for projects that are going ahead or likely to go ahead, that careful integration into the existing process. with optimized heat recovery, absolutely essential. You do need process knowledge when it comes to a heat pump. We're not talking about changing a light bulb in with out with one, in with the new one. It's very much you have to understand the process and how this fits in. Utilizing thermal storage and making sure you use that to balance loads, that's absolutely essential. And that also helps reduce the capex so that you don't have these peak demand issues. Also, there's opportunities with demand flexibility using a heat pump where you can store the heat of hot water or in a large sort of vertical tank. Big opportunities there. We also noticed that implementing the heat pump project, when you're considering other non-energy benefits, is absolutely very important for getting the projects across the line. So if you need extra production, you need extra heating capacity, it certainly helps a lot there as well. And then finally, last but not least, is all about the soft skills. You are talking about a big change program where people are used to flicking a switch on and off for a boiler. There is more complications, and you do need commitment at multiple levels to get these happening. So they're the major findings that we've had from these studies. And so with that, I'd like to hand over to Cordin so we take an even deeper dive into the technology. Cordin's going to take us through refrigerants and applications and what have you. And Cordin, I'll have a go at handing over the presentation to yourself. If we have some trouble, I'll look at the version you've sent me and see if I can give the PDF version a go if we have any troubles there. But Cordin, let me hand that over to you and see how we go with that. Cordin, that's coming through beautifully.
Beautiful. Okay, great.
We're in your hands.
Can you see my screen, full screen?
Absolutely.
Yeah. Okay, great. Thank you, Jarrod, for a nice introduction. I would like to welcome you to my talk here in this webinar. So hello, everybody out there in Australia. So a little bit distance from Switzerland, but with the new technology, everything is possible. So my talk is on supplier update. So what heat pump suppliers are there out there in the market, what refrigerants are used, and some application examples in the food and steam generation industry. First, 2 or 3 publications I would like to present to you. So this is a white paper that we produced recently. It's about strengthening industrial heat pump innovation, especially in Switzerland, for decarbonization of the industrial heat. It's a collaboration work between several research institutes in Europe. So in the Netherlands, Denmark, Switzerland, Norway, Austria, Spain, and so on. So here is a link if you are interested to have more information on that. The goal is to strengthen the industrial heat pumps to European politicians, especially, or stakeholders. Then we have a review paper on high temperature heat pumps. It's a market overview of the state of the art. It has been published in the Journal of Energy, and it got quite a resonance. So it's quite an overviewing paper on that topic. So it's also worth to read. Then we have another paper. It's on multi-temperature heat pumps. It's more a review on literature, but this is interesting because it's possible to make heat pumps not only with one heat source and one heat sink, but with several. So you can imagine several heat sources, one maybe at the lower and one at a higher temperature, and combine it to a more efficient system. So that's a paper there. And then also I have written a book in German language, so it's called Hochtemperatur Wärmepumpen. Yeah, it gives an overview on this topic, and I will use quite a few slides out of this book in today's presentation. So again, I speak about suppliers, refrigerants, and application examples. This is a cake diagram of the process heat demand in the European industry, and it shows it by application. And you see that a big portion, 66%, is in process heating. Then there is space heating, space cooling, process cooling, and then non-thermal applications. And if you look at the process heating part, more than half is over 500 degrees. So it's quite a similar graph like Jarrod showed before from Australia. Also here we have a big portion also in the lower temperature ranges. So 26% between 100 and 200 degrees and 11% below 100. So this is actually the market or the target market for industrial heat pumps. Yeah, that's here. And if you look at the fuel sources, you can also see that there is a big part or the major part on fossil fuels, coal, oil, gas, and at the moment 11% biomass. But other renewable energy sources are just in a small portion as of today. So there is a huge potential to change, to decarbonize the industry. The CO2 emission levels are shown here for different industrial heat technologies. We have here a gas boiler, oil, coal, and so on. And we have here some CO2 emission factors. And we can compare that to heat pumps. And if you look here on the last row here, the CO2 emissions per kilowatt hour of useful heat can be reduced by a factor of 10 if the electricity used in the heat pump is quite renewable. So that's also a huge potential. Now, heat pumps for industry. So you can imagine an industrial company has several industrial processes running. So like, for example, distillation, drying processes, evaporation, pasteurization, and so on. It uses primary energy, which is mainly gas, oil, and coal, biomass, and runs its processes. Then there is a huge amount of waste heat at the lower temperature. For example, some exhaust air, waste water, compressed air. And this is actually not waste. It could be used as a useful heat in an industrial heat pump as a heat source. And then running with primary energy, which is electricity, some processed heat can be produced. So we are closing this cycle here with waste heat recovery, and the heat pump is the major transformator of energy, converting the heat, waste heat to higher temperatures. The efficiency is shown here, is calculated as a coefficient of performance, which is in this case the useful heat divided by the electrical driving power. Here is another diagram of such a heat pump system. So we have an evaporator, a compressor, a condenser, and expansion device, different heat sources. It can also be ground air or some environmental source. Then, for example, cooling heat from a tower, waste heat, and so on, vapor condensation at different temperature levels, and then converting this to heat sinks. First of all, space heating for the buildings, then, for example, drying heat for processes, air heating processes, then also steam, process water. So here again, a cycle of a heat pump and COP definition. When you look at Switzerland, Switzerland is a small country, but we have quite a lot of heat pump sales. In 2019, there were more than 22,000 units. And you see here the distribution as a function of the heating capacity. So between 5 to 13 kilowatts, this is the range where there are the single family houses. And so here we have a market share of more than 90% of the heat supply systems is a heat pump. This is compared with oil and gas boilers here in red. And you see that with a higher capacity, the oil and gas boilers get more in favor. So this is the graph in terms of units. But now we can convert this into heating capacity, so summed up over the whole range. so in kilowatts, so the units multiplied by the heating capacity. And here again, in the small small range, for single family houses, here we have heat pumps, which are dominating. But if you look here at the higher capacities, this is all oil and gas. So it's a big potential to, really a big shift of the industry to renewable heating technologies, and especially heat pumps. So there are several changes to the wider spread of industrial heat pumps in the market. First is quite a low awareness of the technical possibilities which are there with heat pumps. There's also a lack of knowledge about how to integrate a heat pump into systems. Then the bigger heat pumps are also quite tailor-made designs. So it means the batch sizes are small, so it gives low economies of scale. And if you compare it to an oil-fired boiler, the amortization periods are sometimes challenging. So required are 3 years typically, and this depends strongly on the local electrical price and gas price. Then there are other competing heating technologies, not only fossil fuels, but especially, and then there are other renewable energies sources like biomass, for example. Then there is typically a requirement for heat storage to compensate the time lags between demand and supply. And so this makes the integration a little bit more complicated, but there are solutions there. And for higher temperature, there is still some development needed, especially to design and develop compressors which are temperature stable and refrigerants which can be used at that temperatures. Now to the manufacturers, to the suppliers. In this graph, I show you several heat pump products as a function of the supply temperature. So this is the maximum supply temperature the heat pump can deliver, and as a function of the heating capacity in kilowatts. So you see the range of heating capacity is quite large. It starts about at 20 kilowatts, goes up to several megawatts. And then the temperatures go up to 165. So there are products out there in the market which are, these are all commercial products. I have to state note that it's not a R&D. And so there are products there over 26. And the compressors used are for the larger scales more turbos. Then we have screw compressors in blue, and then pistons in yellow. Here are some pictures. This is an Ochsner heat pump from Austria. It can deliver 130 degree here. Then we have the heat booster from Viking heat engines. It goes up to 160 degree. And then Kobelco, a steam generating heat pump from Japan. It goes to 160 degrees. That's the examples. Then what important are the refrigerants used in the heat pump cycles. They are listed here, and you can see that let's say at 90 degrees up to there are the ammonia heat pumps which can deliver that heat large scale. Then we have also CO2 up to about 110 degrees. And then at higher temperatures, there is the R245FA, which is a hydrofluorocarbon, and it is facing phase down due to new regulations of refrigerants. So there is a need to replace these refrigerants here in the top temperatures. This slide gives an overview of these systems. I will skip this quicker. So for the listener which are more interested into the specific systems, I can talk later on or have separate discussion. But what you can see is also the heat pump cycles, which can differ. So normally it's a one-stage cycle, but there are two-stage cycle like cascades, or there are economizer cycles. There are cycles with several parallel compressor arrangements to increase heating capacity and so on. On this slide, there are some other heat pumps shown, and they are all commercially available. In Europe, more or less, it depends on the company how wide or how broad their distribution network is. Some companies have worldwide distribution, and some are more on a local market. This is a table summarizing these commercial available heat pumps, which supply heat higher than 90 degrees. So which is interesting for industrial applications, because this offers new applications potential. And so it's somehow like a small selection guide, let's say. Here you have the heating capacity, then the temperatures which can be reached, and then the refrigerants and the products and the countries and compressor types. Now about the efficiency. You know, the COP, as I showed before, is the useful heat divided by the electrical power consumption. And typically we have a COP of 4. So it means 1 part electricity gives 4 parts useful heat. And this at a temperature lift of about 40 to 50 Kelvin. So the temperature lift is the temperature difference between the heat source and the heat sink. So we have a waste heat, for example, as a heat source at 40 degrees. And then we have a 50 Kelvin lift, which gives 90 degrees heat sink. So a COP of 4 or 3 can be expected. And this is thermodynamics. We cannot go over that. The COP decreases with a higher lift. So that's a fact and has to be considered. So here is a fit approximation of that black line, which could be maybe used for some first calculations. This is another graph of the Kobelco steam generating heat pump from Japan. It shows the operating map as a function of temperature of the steam and as a function of the heat source inlet temperature. So this model can reach almost 170 degrees at the 70 heat source. So the COPs are around 2.5 and 3.5, and this system can produce 0.5 tons steam per hour. So here again, I will skip that because of time reasons. I want to emphasize also some other systems not shown before, but they come up recently. For example, the rotational heat pump from ECOP. It's a company in Austria. This is a different process. It's using the Joule process. There's a gas in these tubes, and these are circulating, so rotating, and the centrifugal force forces the gas to the outside to a higher pressure. Here we have a high temperature, the heat transfer there, and then it goes back into the center. It's driven by a ventilator here. It's a noble gas which is circulating in this system. And then here at the lower pressure side, more in the center of the rotational axis, there is the low temperature heat exchanger. So this is a quite unique system, can reach 150 degrees and is flexible in temperature ranges. So for sure worth to investigate in more detail. Then here is a slide from Siemens. Siemens is a big company, and they offer quite a portfolio of high temperature heat pumps, and especially in the megawatt heat supply range. So you see here the size, if you compare it to a person, these are big plants, and they can deliver that heat, and the applications are for bigger cities, heating of large communities. Then I would like to show this slide. It's from MAN, Energy Solutions in Switzerland. It's an electrothermal energy storage system. This also a very large system. The smallest is 5 megawatts thermal energy. And the core of this system is the Hofim compressor. It's coming from the gas industry, and it's using CO2 in a cycle of heat pump cycle, and it produces heat. It can produce cold, and it also can produce electricity when reversing the cycle. So it's called a 3-generation system. Also very interesting to look at if you are in very large scale. As I said before, there are some market challenges, especially the electricity to gas price, and these are the gas prices in Europe. You see it by color. So if the electricity is cheap and the gas is expensive, the ratio is small. So this means it's in favor to heat pumps. And you see in Scandinavian countries like Sweden, Norway, and so on, these are quite low, and there are a lot of heat pumps installations. Then there are other countries which are more in the middle, 2.5 ratio, 3. The European mean or average is around 3.2, I think. So then there are countries where the gas price is so cheap, like in the UK, where it is quite hard to compete with a heat pump to a gas boiler. So these are values from a smaller industrial end user. Then another challenge is the costs for installation, the investment costs. And here is a graph showing the investment costs specifically also in euros per kilowatts of heating. And this is a function of the heating capacity. And you see it goes down with higher capacity, and with typical systems of around, let's say, 200 kilowatts to 300, 400, 500 kilowatts. We are in this range of around 500 euros per kilowatt. So, for example, Viking heat booster costs around 100,000 euros. It delivers 200 kilowatts, so we would be here. And so it's about 500 euros per kilowatt. This is a rough calculation. Then there are other factors for the decision to invest into a heat pump system. And yeah, these are various factors, financial factors, return on investment, and so on. Then the operating costs, as we saw before, the electricity prices. Then also the mind setting of the company. If they have a green image from the vision of the company, has a major impact on the decision to go into renewable energies. And then there is the legislation. There is the F-gas regulation, for example, which regulates the refrigerants. Then there are CO2 emissions to consider, and all these targets, they are here. So I'd like to summarize this first part. So there's quite a large application potential for hot water, hot air, and steam. There are different applications in different industries. We'll see that later on in the second part, more visualized. In Europe, there is a potential between 100 and 150 degrees, which is a target temperature for industrial heat pumps at the moment. Then there are many products available from several manufacturers, and they can provide heat higher than 90 degrees. Some pioneers reach, let's say, 165 degrees. The COPs are in this range, and we can approximate it with a fit formula. The heating capacities are quite broad, and the refrigerants used are mainly shown here. So dominated by R245FA, hydrofluorocarbon. Then we have ammonia, CO2, and then R134A, and already some hydrofluorolefins, so HFOs. The compressors can be screws, turbos, or piston. And the cycles are typically one stage, but improved with internal heat exchanger designs, with parallel compressor, economizes cycles, or cascades. So I think, Jarrod, here we can make a quick break, if this is okay.
Absolutely. Give you a rest there, Cordin. Thank you. Very interesting start there. Just to encourage the questions, that we might take a first question already. We've got one from Ahmad, and it's regarding the heat pump capacity and if it degrading with low ambient temperature. So do you always have to have a boiler as a backup? From a European context, Cordin, what do you guys see over there?
Yeah, I think most industrial companies today have a gas boiler or an oil boiler installed already. So it makes really sense to have it as a backup, and not only as a backup, but also for high peak loads. So this is a typical installation which you also see here in Europe. And I think it's a good combination. So to combine a heat pump also with a gas boiler, if it's already there.
If it's already there, indeed. Question there from Don. Is the dollars per kilowatt, you showed euros per kilowatt before, is that affected much by the temperature lift, or is it just the absolute number of kilowatts?
Yeah, these are numbers which are showed, which is covering quite a large temperature range. So I don't have too many data actually on that. So it would be interesting to look it in more deeply. Yeah.
I think but most of them you're looking at about a 50 or so degree.
Yes, most are so around 50. This is a typical temperature lift, which is economic, let's say, economical.
Yeah. I guess as we see more operation of these higher temperature ones or very high temperature ones, we'll get more data on that dollars per kilowatt as well.
Yes.
Very good. Just checking on our panel, if there's any other comments on those questions there from our panel about that. Let's see if anyone would like to come off mute and have any comments there. No, looks like we'll keep on moving then. Cordin, back to you. We're on to suitable refrigerants, so hand it back to you.
Okay, so you can see the screen well?
Absolutely.
Absolutely. Okay, good. Then I continue. So on this graph, I tried to summarize the most refrigerants used as a function of the heat source and heat sink temperature. And so you can see here, it starts at 0 degrees, goes up to 100 degree, then 200 degrees. And then you see at the highest temperatures, it's water. So water steam is the most efficient refrigerant. Then we have CO2, ammonia, CO2 up to around 120 degrees, let's say, because of the transcritical cycle. Then we have ammonia, goes up to 110 degree heat sink temperature. This is limited, let's say, by the compressor maximum pressure, which is increasing. So 70 bar, for example, or more is possible today. Then we have hydrocarbons, so pentane, butane, and propane, and they are suitable for higher temperatures, over 100 degree, especially pentane. Okay, they are natural refrigerants, but they are flammable, so that needs to be considered in terms of safety. Then there are some synthetic refrigerants, used like R365 MFC or R245 FA that we saw before, which is like state of the art for heat pumps today, but they need to be phased out. There is a phase down, let's say, and the replacement fluids are synthetic hydrofluorolefins like HFO, like these numbers here, and they will be the suitable replacement fluids. And then at the lowest temperatures, or let's say lower, yeah, 80 degrees condensation, there are these fluids here replacing R134A. So these fluids could be used also in a first stage of a cascade, for example, for cascade heat pump. This comes all because there is a big debate on refrigerants out there. Yeah, there were 4 phases, let's say, or 4 generations of fluids, working fluids, and now we are at the 4th generation, and this is about GWP, so global warming potential. It has to be low, as low as possible. Before there was the discussion on the ozone depletion, and now it's on global warming potential. And so these hydrofluorolefins, HFOs, or hydrochlorofluorolefins are there, and they are tested. At first developed, tested, and now more and more commercialized. So they have very low GWP, very short atmospheric life, low flammability, and efficient. And for high temperature heat pumps, a high critical temperature, which allows condensation at higher temperatures. Here, this slide shows an overview of some manufacturers of refrigerants, and yeah, they are interested into delivering synthetic refrigerants. So there's several companies active in this market. The selection criteria are shown here in this table. You have the thermal suitability, which is important, environmental aspects, safety, efficiency, and availability. And then there are other factors, also oil solubility, thermal stability, and so on. These are the materials compatibility. This also needs to be considered and tested. So there's always a combination between the compressor manufacturer, the oil supplier, the refrigerant supplier, and then the heat pump manufacturer. So all need to sit on the same table to decide on the system. This graph shows the safety group classifications according to European norms or American ASHRAE standards. So it shows the flammability as a function of the toxicity, and ideally, in ideal situation, should be here in this lower corner, A1, which means no flame propagation and low toxicity. And there are quite a few refrigerants there, but there are some others which are with a higher toxicity, like for example ammonia. So here some safety measures are needed, and here in the higher flammability, A3, these are the hydrocarbons. This table shows a more broader overview of refrigerant properties. So these are refrigerants which were considered for high temperature heat pumps. And so the orange ones are excluded, which means not in consideration anymore, because either they have too high ozone depletion potential or the global warming potential is too high. So there are the yellow ones, which are which we, especially at the university, also investigated in more detail. So I just skip this. It's a little bit a lot of information, but gives a good information as a background information. This is another table showing the properties of the HFO, HCFO refrigerants and the ones we tested in our lab, in our heat pump. So what is important here is, yeah, the GWPs are small, so smaller than 1, 2, smaller than 10. The lifetimes in the atmosphere, if they would go into atmosphere, this is in the order of some days. So it's very not likely that they will reach the stratosphere to generate, for example, some pollution there. Then there's the safety group and so on. So the chemical structures you can see here, they're quite similar. Just here the chlorine atom for the HCFOs, and here we have the hydrogen. And these are 4 carbons and these 3 carbons. So there are some research gaps for high temperature heat pumps. First, as I said before, it's testing new refrigerants and new possibilities. Also the application of natural refrigerants, so like hydrocarbons, CO2 or water. So there's a huge research activity in this typical area. Then in general, extending the temperatures to higher values on the heat source and the heat sink. In principle, so what we have in the single family houses to make hot water, we want to transfer that to industry and to higher temperatures. So then we have the improvement of the efficiency. It can be, the heat pump efficiency can be improved by multi-stage cycles, oil-free compressors. Oil-free compressors are very interesting because then there is no need for oil management anymore. So the heat pump cycles can be designed in different ways and more efficiently. This is also an interesting research area. Then the components need to be developed which are temperature resistant, new control strategies, and then scale up the functional models to industrial scale. So there is quite a lot of research needed still in this area. And our focus at the university is especially testing such new refrigerants. If you look at the number of publications in the area of high temperature heat pumps, you can see this curve over the years. So here the activity of research was quite high in 1980, so in the oil crisis, then it goes down over the years, and then around 2010 it increased again, and it is still high today, even higher. And before this activity was correlating quite with the oil price, but now in the last years this is not the case anymore. So this means even if the oil price is low, the research activity in energy research and especially heat pumps is still high. We have a heat pump in our lab in the university in Buchs in Switzerland at NTB. It's a system which can produce heat from 80 to 150 degrees. It is investigating the hydrofluorolefin refrigerants, and we have data now on this, and we have publications on this research. This is a water heat pump, one stage with a piston compressor, and it can produce up to 10 kilowatt heating capacity. Here is a graph of the COP, which was achieved with these 3 refrigerants as a function of the sink temperature and as a function of the temperature lift. So let's look at the 50 Kelvin lift. These curves here, we have that called as a reference point. So here at this point, the heat source is 60 degrees, which could be an available waste heat from industry, and then lifting this up to 110 degrees, so it gives 50 Kelvin lift. So then we reached a COP of around 3.2 with the internal heat exchanger design. So the comparison of the refrigerants shows that the efficiencies are quite comparable in the measurement certainties of this system. At lower temperatures, there were some more differences, and there is a fluid like this one which has a critical temperature of 171 degrees. So here we could have reached even higher temperatures, but not with this system, which is limited to 150 degrees. Another interesting area of industrial heat pumps is steam generation. It offers much more applications. And now you can consider, let's say, new solutions, or so you have here a tank with water, and before you have gas to evaporate this water. But now you can replace the oil and gas system by a heat pump, by a high temperature heat pump, which uses waste heat as a source or some other heat. Maybe you can also have a multi-temperature heat pump using even ground source heat, and then evaporating the water here to produce low pressure steam. And then in a second stage, you have the water steam cycle. You can recompress it to higher pressure. So you can reach higher pressure steam. This is just a schematic how this can be done. And then the input is water, normal water, which can be expanded also here a little bit to have under pressure in the tank. And then you need to consider some water intermediate cooling between the compressor stages. That is all, and in principle easy to do. We have made a system here in the lab, and it shows this system with the tank, with the heat pump as for evaporating the water, and then the steam is recompressed in one compressor to generate steam at 115 degrees, so low pressure steam, just as a proof of concept to do that. Then there are many research groups around the world in this area investigating high temperature heat pumps with supply temperatures higher than 100 degrees. So you see here a list, a table with these organizations, the partners, countries, the cycle which is used. So you can see there are European countries, Austria, Switzerland, Germany, France, which are active. Then we have Japan. And this is structured by the temperature which the heat pump can deliver. So 160 degrees, and then it goes down. You have information on the compressor, the refrigerant, and you see there are some refrigerants which have an unknown chemical composition. So there is research activity in this field. This table continues here on that slide. So we have groups in China, Japan, Netherlands, Korea, Norway, and so on, which are all active in this field. And I think in the last years, we all met more or less at conferences, and we review papers from each other. So it's very interesting to work together internationally. So we can conclude that part. So I would say there's a worldwide high research activity on high temperature heat pumps. So several groups are there active in different countries, in European countries, but also in Japan, Korea, China. Maybe also in Australia. I also maybe missed that in this overview, but for sure there are activities there. Then the capacities are more in lab scale for the research studies, but there are already some projects which are in pilot scale, prototypes up to higher than 100 kilowatts heating capacity. The COPs achieved, so the efficiencies are even higher than the commercially available heat pumps today, so which is a good sign. So there is room for improvement to push this limit of efficiency also to higher values. And there is a trend to use natural refrigerants like butane, pentane, CO2, water, and on the second part, synthetic refrigerants like hydrofluorolefins, which have very low global warming potentials. And these are these refrigerants here with these R numbers. The cycles, the heat pump cycles used are mainly one stage, but they can also be optimized with internal heat exchanger designs, economizer cycle, and so on. Mostly piston compressors are used in lab scale. And in our university, in our system, we tested hydrofluorolefins, and we also increased the FCOP by including the internal heat exchanger. So it's an important component, I think, to design heat pumps. And we could demonstrate also okay, these typical applications in which would be useful for industry. So like in waste heat recovery or steam generating or drying. So these are the major applications there. Now, some application examples. First, this slide, please remember, or let's say this is important. We want to make hot water, hot air, or steam. Very easy to understand, but there are many applications there in the food industry, meat industry, bottle, wine tanks, so for washing and cleaning, for example. Then there are hot air, so drying processes for different foods like starch, pet food, and so on. Then steam for sterilization, pasteurization of foods, like in the milk industry or a fruit juice industry. Here is a slide which shows the temperature levels of different industrial processes in the food and beverage sector. So you have processes like drying, evaporation, and so on. And they are shown here as a function of the temperature range. So it goes up to 200 degrees. And so this shows the potential. If you have a heat pump which can deliver 80 degrees, so all these processes can be processed with heat delivered from the heat pump. But if the heat pump can reach 100 degrees or 140, even bigger portion of this energy can be delivered. So this shows also the potential. And this can be done also for different sectors, not only the food and beverage, but also paper industry, metal, chemicals, wood industry, textiles, plastic, or and so on. For drying, there are also temperatures which are typically used for different foodstuffs. So here is the drying in air inlet temperature. And we have here, for example, milk. Milk is at high temperature from 170 degrees. So if you have a heat pump which can deliver 160, this could not be made. But at least a heat pump could be used for preheating the air. So, but there is a need for higher temperature. But there are some other products where the heat pump could deliver the heat for the drying air directly, especially here in these areas of here, tomato paste, potato, starch, all this industry can be very interesting. In the food and beverage industry, as I said before, there are different applications which have a potential. Sterilization, washing, pasteurization, wine tanks, cleanings, and so on. Steam, hot water for slaughterhouse cleaning. So the meat industry can have a potential here. Then we have pasteurization in the cheese factories and hot water. Then we have again drying processes, as I said before. It can also be brick drying. So the air preheating at least to 120 degrees first from moist air as a heat source from the exhaust air. Then the wood drying is an application similar approach, starch drying. Then animal feed. Then spray drying industry could also profit from a heat pump to reduce energy consumption. And then paper industry, for example, low pressure steam using the cooling water and humid exhaust air as a heat source. Then there are more applications for industrial heat pump, district heating networks. So where the networks are installed already and the hot water production up to 120 degrees is necessary. Here it has a potential. Also hospitals could be a potential area for steam production, for autoclaves, sterilization, laundry drying also. Then the PET bottle industry for process heat for the injection molding of plastic preforms. Sugar industry to process heat, process sugar beets, and also have steam for other production processes. Then there are more applications here, like in breweries, for the brewing process, which needs heat at 100 degrees, for mashing, lautering, wort boiling. Milk processing industry, so it means pasteurization at high temperature, so ultra high temperature pasteurization, very short time, but in seconds, but in a continuous process. Chemical industry for distillation of alcohols, bioethanol, for example, in distillation columns. Or last but not least, wellness and sauna could also be an area for a CO2 heat pumps, where there are different temperature levels in the sauna, and with the transcritical process of CO2, these temperatures can be delivered quite efficient. Okay, I have more slides on applications here. Yeah, this is a slide showing the cheese production in a cheese factory in Switzerland. It uses the waste heat from a data center. So data center computer, for the computer cooling, this waste heat goes into a district heating network. It goes into a cheese factory, and the cheese factory has a big energy demand to process the milk to cheese. And a heat pump in the cheese factory is transforming this heat from the district network to process heat. So it's shown here. We have the data center, the district network, we have the heat pump, and then we have a hot storage tank. And it has different processes in the factory. And with the heat pump, so the space heating can be provided, the hot water, and also process heat. And there is a gas boiler as a redundancy, and to cover the peak loads to process heat at 105 degrees. So it's it's a good example where a heat pump and a gas boiler are combined. Yeah, here is another graph showing how they installed it in their company. The heat pump used is Ochsner heat pump. It's shown here, has 520 kilowatts. It's using an economizer cycle and a screw compressor, two-stage. This heat pump cycle is beneficial to have for high temperature lifts. And it uses a hydrofluoroolefin refrigerant already with a low global warming potential. It's going into operation very soon, or is already in operation. Here are some performance data from water 18 degrees heating up to 92 degrees, which gives a temperature lift of 74 Kelvin, which is quite high. And the COPs reached are in this area 2.85, 2.55, depending on the part load. Other application in Switzerland, which is very interesting, as we are quite famous for chocolate, is in the chocolate factories. Also here we have a lot of heating and cooling demands, and so heat pump can be a good heat generating and cold generating system, combining both sides of the heat pump. I don't go into more detail here because of the time reasons, but there are some papers around which show this in more detail. Another application in a company in Switzerland is here in the beverage industry for processing water for disinfection of the filling plants and wine tanks. It goes to 95 degrees. It's used for that. It's also an Ochsner heat pump shown here with this heat capacity, and there is a heating COP of 4.2.
And Cordin, just wary of the time now, I thought, why don't we go through a couple of questions here, and then we'll go through the speak to the guys from Alliance, and then if we have time, we'll get back to this. I know you had an example for a slaughterhouse or abattoir there as well. We've got a few people be interested in there. If I just take a couple of questions there, there was we got a question here from Carl Duncan asking about globally any heat pumps are being used for process steam. Are you aware of any of those examples you showed before? Look like just lab scale. Anything being used for a proper industry type process steam applications?
Yes. So like the system from Kobelco, from the Japanese, they produce the heat pump for steam, and their applications are the ones which I just presented here. So low pressure steam for different industrial companies. Yeah, it's for sure not a mature market. It's a new market, and it's quite also interesting for the companies to go into this market. And now it's time to gain a bigger market share. So now this market is small, but as a first mover, it would be possible to get first bigger market share. Yeah, I can talk to the person in more detail maybe later on to have more specific conversation.
Good, and look, I think we're happy to go after our allotted time here today. We can do that and take that a little bit further after 5:30 today. So happy to take that as well if you're happy to stay on. Because there's more questions about, you know, what is a prototype and lab research versus commercially available. Maybe what we'll do is towards the end we'll go back to some of those slides, I think around 45 and 46 here from Peter, and just go through those maybe in a bit more detail, and we'll see what's available now and what's not.
Yeah.
And question here from Kuba, when might you guess commercially available high temp heat pumps will deliver a COP greater than 3.5? And from what we're seeing today, I guess if the COP is a function of temperature lift, then I guess we're not going to see some sort of magic to adjust that. But high temperature above 3.5, what's going to drive that, do you think?
So the thermodynamics cannot be overruled, let's say. It's the Carnot efficiency, like shown in this graph. So 3.5 is reached at the temperature lift of around 50 or 60 Kelvin, so lift. So this means this is the reality. It cannot be higher.
Can't get around that.
I think I kind of not around that. So maybe the second law efficiency, which is like the comparison between the Carnot efficiency. Now it's 45%. Maybe this increases with better compressors and better designs to maybe 50%, 60, maybe 60%. Then we can reach COP 3.5, 60 Kelvin lift, 765.
I think that graph there is a really good summary of what's possible. So that'll be a great resource for people to refer to. Good one. Got a question here from Ahmad asking about commercial heat pumps with oil-free compressors. Saying are they currently what's available there? He knows about some problems with don't work at high condensing temperatures. And what's the maximum temperature that these oil-free compressors can do, and maybe our panel might be able to chime in here and help a bit as well.
I know that there in this area is a lot of research activity, because if we can leave out the oil, that makes everything much more easier. And from other industries like gas compressing industry, that the technology is there to compress gases, so that's for sure. And if you can leave out the oil, there is no oil management anymore. The oil also, so I mean, the heat transfer in the heat exchangers gets better without the oil. Yeah, and you have no problem with oil degradation. So there is you can go to higher temperatures. And for sure, there are challenges in designing these compressors for higher temperatures. But I expect in the next few years, there will be compressor manufacturers which have such systems on the market.
Very good. And you mentioned earlier about Viking heat pumps. I think we've heard that they had gone into administration or something. Are they still supplying in Europe, or they're still going?
Yes, they had some financial difficulties, and so now the technology, as far as I know, has been spin off to another company in Germany. It's called something space heat, process heating, or something like this. So the persons which were active with the Viking heat pump booster technology, they spin off to another company and provide that technology there. So that's hopefully not finished. So it still continues.
Good to hear.
Because they are quite pioneering in this field.
Good. What we might do now is let's move on to a wider panel discussion and start looking at a bit more here and now what's happening. Before I do that, I thought I might launch a poll with everybody and just ask the question. And I think this will launch. I haven't tried this before, so bear with me. Just asking the question about in your business, who is the key enabler to get heat pumps adopted? And we've got the option there for operations manager, maintenance manager, engineering manager, factory workers management, or all of the above, if you want to do that. Oh, it looks like the poll's started and we've got some answers there already and coming in the maintenance, but feel free to answer that one. We'll share the results for that in just towards the end of the presentation and see what we say. Who's the one that is going to be need to convince here to get heat pumps moving. So we'll look out for that one a little bit later. Now, with that, I'd like to open up for our panel here. And Mike, maybe we'll start with you from EECA. You've been running a program to get heat pumps and what have you established in New Zealand. Maybe it's a 1 or 2 minute overview of that, and then we'll have a chat to the guys from Alliance of their experience. Mike, are you there?
Great, yep. Thanks, Jarrod. Yeah, so I guess EECA, its purpose is to mobilise New Zealanders to be the world leaders in clean and clever energy use. That's quite a noble and big goal. And I guess it's long recognised that heat pumps can play a role in helping New Zealand achieve that objective. And so like Australia and Switzerland, use of process heat is a big cause of emissions. And so in New Zealand, we think that in that sort of food processing space with steam and hot water, about 3 million tonnes of emissions are produced annually, which is about 9% of our energy emissions. And so, and about half of that is thought to ultimately be a use of sort of 100 degrees or below. So with that in mind, EECA's Technology Demonstration Fund, it was thought that making that a priority to try and get more experience in installations of heat pumps to sort of meet those needs would be one thing we really could do to help push us along. So, I mean, EECA's for a long time has provided information and guides and things, but really there's nothing like practical, actual demonstrated experience, as I'm sure we'll find out very soon. And so since 2018, 6 installations have been funded, 4 completed, and of those 6, 3 were in meat plants. Only one of those is actually finished so far. The others are sort of on hold for COVID or other reasons, sort of missing windows for installation, but hopefully will progress fairly soon. And yeah, I guess it's just the meat sector is that sweet spot of there is waste heat available from refrigeration kit, and it ties in really well with some of the available technology that you know, based on ammonia that you can use today. And perhaps if we talk at the end, I don't know, I guess the future in some ways, the silver lining or the bronze lining of COVID is that as part of stimulus efforts, there is more money available to try and push out new decarbonisation technologies and things, and of which heat pumps will certainly be one of the factors in the mix. So yeah, I'm really keen to hear what the guys from Alliance have to say as well about their plants. So I think I'll hand over there.
Fantastic. And if that will be Doyle or Brian, I hand over to you to take us a bit through about the project that you've undertaken for Alliance Group and some of the implementation drivers and how you're going with the project.
Okay, thanks Jarrod and Michael. So as Jarrod just mentioned at the start there, I'm actually the group environmental manager, so I don't have an engineering background as such, but I'm responsible for the, I guess, the utility side of the business, utility performance. So and Brian's and Grant there have got more of the engineering now than me, but I guess just to quickly touch on what Alliance is. We're a large red meat processing company. We've got about 7 plants throughout the lower South Island and lower North Island of New Zealand. So we process sheep, lamb and beef as well. So we use quite a lot of process heat for wash water, so hand washing, apron washing and the like. Also, so that's sort of your 40 degree water. We also use clean up water. So cleaning up rooms after processing, which is about 60 degree water. We also use sterilisation water as well, 82 degree water for sterilising knife equipment and things like that. And we also have rendering processes which require requires steam. Nelson is one of our smaller sites, and we don't have a rendering operation there, so it's really just a site that needs hot water. So we at that site here we process sheep and lamb and also bobby calves, so basically small cows, I suppose. And so previously Nelson, the Nelson plant has generated all its hot water used for hand washing and sterilisation, and that using a diesel fired boiler, a 1200 kilowatt boiler. And a couple of years ago, 2017, there became an opportunity for us to export our bobby calf carcasses into the US market. But to do that, we needed to sterilise the calf carcasses with 82 degree water for a period of time for sterilisation to kill any bacteria and that on the carcass. So getting into the US with these bobby calves enabled us to generate more revenue, and so but the existing diesel boiler there that we had didn't have the power, I suppose, needed to provide that spray wash water. So we were considering installing a second 700 kilowatt diesel boiler, but we've got some energy consultants, DETA, that we do a lot of work with in conjunction with EECA, and they suggested that we look at a high temperature heat pump. And it was sort of quite a last minute decision, but you know, we looked at the numbers in terms of the revenue that we could generate from getting these calf carcasses into the US market. The diesel boilers, the diesel over here is about 87 cents a litre, so for gigajoule looking at about $23 a gigajoule. Our power price is about 13 cents a gigajoule, so about 13 cents a kilowatt, or about $33 a gigajoule. So when you look at I guess those input energy prices, electricity is a little bit more expensive than diesel, but when you take into account the COP, it actually become quite a lot cheaper operationally to look at the heat pump option. So that the air provided. So when we, I guess, invest capital, we look to get a quick return on our investment, 2 or 3 years, and looking at that with that sort of savings in electricity versus diesel, made that stack up along with some government funding support through as new technology demonstration fund. So and obviously there's some carbon benefits as well. So those were sort of the, I guess, the drivers for putting the heat pump in. So yeah, more revenue, cheaper operating costs, and also the carbon benefits as well. So I've got Brian and Grant are probably sort of best to talk about perhaps the challenges with installing the heat pump. I've got actually I've got a photo, if you like, Jarrod, that I can share.
Yeah, you share the screen, absolutely, and then
the heat pump.
Get Brian and Grant to talk about some of the challenges they come in. No engineering project is ever completely smooth, that's for sure.
So that's it. Can you see that there?
Looks beautiful.
Yeah, nice and shiny.
Yeah, no, it is a beautiful thing.
And Brian, all smooth sailing the whole way through the project, or?
That's half. Yeah, that's actually half of the pump, and
So,
the bit that you can't see was sort of attached to that skid in the initial concept, which sort of ultimately became our biggest challenge, was fitting it into the space that we had available. The initial skid, we couldn't even get it into the room. So that was, I guess that was an oversight initially. I didn't really have a very good perspective of the size of the machine. So when Grant and when Active started arriving with these CAD drawings, and I started walking around with a tape measure, yeah, we were it was kind of comical, because yeah, it wasn't going to fit. So we a lot of toing and froing, and the support from Active came up with sort of several different ideas and designs, and we ended up sort of splitting it in two, and that's the compressors in our what we call the engine room, and the high pressure. There's a control there, is it? Yeah, that's on the that's actually on the roof of the engine room. So in hindsight, I think we ended up with kind of the best layout for our operation. The plate heat exchangers are behind that vessel. Yeah, so that was.
I guess in your mind, you were thinking originally about a diesel boiler with a footprint of sort of 1 or 2 meters, and you've ended up with quite a large piece.
Yeah, it was quite a vertical bit of gear as well. So the height was an issue with the existing liquid and gas lines in our plant room. It was just yeah, it was quite a major hurdle, really. So,
and this has been tied into your existing refrigeration plant as well, so that you're using that as a cold sink, the heat rejected from the refrigeration plant.
Correct. Yes.
Yep. Yeah, no compressed ammonia. Yep.
And you're aware of the COPs that you've been able to achieve on this?
Yeah, we are. Yeah. We certainly hit 5. We're going, our incoming water is sort of 30, 35 degrees, and we're pushing out, we're delivering 80 degrees to our, to what we call our 82 degree tank. But that's sort of, that's our sterilizing water. So that's what we're pushing back to that vessel.
And just while we're there, guys, our poll results have come through and saying the most important people to get on board, or the key enabler being management. Was that the case for Alliance as well? I mean, was it saying that the maintenance manager, hey, no worries, this is just like another piece of refrigeration equipment, I'm okay? But was it management getting them on board to get in, for the installation? Was that your biggest challenge?
It all happened quite quickly, to be honest. It was the capex had basically been approved for a new second-hand diesel boiler, and it was Alliance is a pretty, I guess, flexible, agile organisation, even though we're fairly big. But I guess it's has some benefits in that you can quickly sort of tap into the guys at executive level, and basically it was a matter of myself and our consultants convincing our group corporate engineering manager that this is something that should be looked at, and then he took it to our general manager for manufacturing, spoke to him, and yeah, said this is sort of the situation, this is the paybacks we can achieve and the benefits, and it was a decision made pretty quickly, I suppose, and probably shocked Brian a little bit at the time, because he had a diesel boiler all ready to go, so it was probably something that was, I'd say, in terms of looking at the heat pump, was something that was driven by corporate. But Brian came to the party pretty quickly, I think, and has obviously been able to make it work on site, which has been great.
What I might do now, guys, if we don't mind, I'll just finish off a few formal slides there, so we make it on the 5:30 in case that people need to leave, and then we'll go through some Q&A for say 10-15 minutes at the most after that, if that's okay.
Actually, Jarrod, I had a bit of a spreadsheet there just to show, I guess, the benefits that the boiler, the heat pumps provided in terms of how our electricity and fuel use has changed over the last 12 months as well, if people are interested in that at the end.
I think that would be fantastic to share, absolutely. Let me just finish off a few little formalities here for everybody. That should come up there for you now, and then we'll take a few Q&A. I think we've got about 6 or so in the waiting there for the questions. So just here, just to say for people to get started, kicking off a study is probably the best way to do that. And I've got a list of consultants here in front of you who have done this already. So they are now got some experience and can very quickly, with say a $5,000 assessment of working out quickly your heat loads, your energy usage and electricity coming on site and some limitations. Very much a quick back of the envelope, and they can rather quickly come up with a likely feasibility estimate there. And then after that, somewhere around about a $20,000 to $40,000 feasibility study is probably then appropriate to then be able to get to an FID. And making sure that's well integrated, that design is going to be crucial to having the good return on investment for sure. Plenty of help out there in Australia with grants that are available. So we've got the Energy Efficiency Communities program there for larger business, got to be above 0.05 petajoules, but that's up to $25,000 to help you with that study. That's available, closing in 24th of September. Encourage people that I think that would be a great one to go for, to get your study funded by the government, to see if we can get into that as well. Also with ARENA is the one that has sponsored the program that A2P's work with. They're funding such solutions. They're looking for all renewable energy solutions for industry. And this is certainly, heat pumps is one that they're looking at. And as long as that power is delivered by renewable energy via PV or PPAs, then they're interested. Peter Henke is the one that takes such inquiries. So I've got Peter's email there. I really encourage you to get that off to them as well. Another alternative, what's coming up as well, the Australia's largest ever cooperative research centre called Race for 2030. They've got a stream dedicated for electrification of process heating. We expect studies and more funding to become available through Race for 2030 over the next few years. That one's just ramping up now, so certainly keep an eye on that one. What else we've got coming up is a heat pump technology selection guide. Help you quickly determine what's going to be the ROI and help you choose the appropriate technology. We're going to bring all the examples and learnings from today and put this through to a study, and also learnings from our feasibility studies, and put that into one package for you. And that's really going to help you doing those back of the envelope calculations and making sure that you understand the ROI impacts and get on top of those early. So that's on its way. We're going to have a webinar on that on the 8th of October, and I encourage everyone to come along, and we can go through this certainly in more detail on the 8th of October. And with that, we've got coming up, this is a very quick schedule of what's coming up for A2EP. So we're doing an end user network meeting, energy price, government grants and what have you. So we'll be able to go into further about these government grants on the 17th of September. I think we could also take a quick look at finance. These EUAs are becoming more available. So we'll be able to take a deeper look at that one on the 17th. As I mentioned before, the industrial heat pump selection guide on the 8th. We've also got now coming up on the 15th of October, we're going to take a good look at metering. Very hard to make a decision without the right metering and information. So let's have a look at the latest technologies and enablers there. And then draw your attention to the 9th and 10th of November. We have our annual Innovation Exchange Conference, where we'll take some deep dives into some more technologies and investment opportunities and what have you as well. So that's coming up on the 9th and the 10th of November. Normally over one day, but we're looking at, say, 2 days or so due to COVID and distancing there. And then finally, towards the end of the year, the end user network meeting, another one on the 19th of November. And again, we'll be looking at energy price trends, government grants, and informing you all on that one. So if you want more A2EP, very, very simple. Just go to LinkedIn, type in A2EP and start following us, and you'll see more coming into your news feed there. We're always keen to say once, twice a week, you'll see us sharing different cases that we think will be really relevant and really important to you. So for those that do need to leave now, it's pretty close to 5:30, a little bit after. Thanks for joining us today, but also hope you can stay on. We're really keen to have go through a few more of the Q&A, and that's what we'll do that now. So a little bit rushed at the end. We're always trying to get through lots of content. Why don't we take through a few more questions and things as well. Just before we go to the open general Q&A, Tony Kimpton, if I could ask you to come off mute. One thing that I keep hearing coming time and time again when it comes to heat pumps is, operation during winter. And the impact of that, and it came up before. Do you need to keep a backup boiler, that sort of thing? Tony, you've been modelling a lot of different scenarios. Aquatic centres seem like an absolute no-brainer for heat pumps. Take us through what you're seeing for this low temperature, maybe myth around heat pumps.
Well, at this stage, there are products available commercially for heat pumps that operate down to 0 and even below 0 degrees. They're pretty clever pieces of kit. They're actually using some of the heat that you're producing to defrost. Virtually, what they're doing is defrosting as they're running. So they're using some of the heat producing to defrost the coil as it's running. So it makes it less efficient, of course. So you use some of the heat that you would normally be putting into your water and into your system. It's tapping off a little bit of that to defrost at the same time, but it does allow it to run down to much lower temperatures. Yeah, and the other option is if you've got a big enough system and you've got enough flexibility, you can actually store heat in storage tanks, so that during those really low temperature times, you can actually draw from that heat and take your heat from there rather than from the ambient.
So that would be a case of 3 in the morning till maybe 9 in the morning or something like that, where the ambient might be low 5 or 10 degrees. Okay, then it's not running as well. You don't push the system, but in the outside those hours, you'd be building up your thermal storage, that sort of thing.
That's right. If you put a larger heat pump in, even it can run during the day while you've got solar, while you've got more power, more renewable energy, and heat water to store that you then use in the colder periods at night and early morning. And you just need to get the balance between the size of the equipment, the size of the tank, and the ambient temperatures that you're working with, and it's all possible.
And I've got a question there from Laura talking about water-to-water systems, both heating and cooling. What do you see as the best opportunities for doing both the heating and the cooling there?
Well, that's one fairly close to my heart, because that's with Smart Consulting. That's what we're working at the moment with a lot of in the field of aquatic centres. So in an aquatic centre, they have majority of the requirement is heating, and the highest peak of that is in winter. There's always some heating that's required, even through summer. But then in the height of summer, of course, you have a fair amount of air conditioning requirements too, for the rest of the aquatic centre, for the gyms and workout areas. So yeah, there is that variation in requirements from heating to cooling, and both at the same time. And there's a point where I guess in the spring, in autumn, you might get an hour or two during the day when what I call heat pump nirvana, and that's when your heating and cooling basically match exactly, and you're not wasting any heat, you're not wasting any cooling. You're putting all the heat into the pool that comes out of the air conditioning system, and everything works just in harmony. And with tanks and other storage possibilities, you can make that nirvana last for quite some time.
Because certainly the COPs we were talking about when Cordin was presenting, that was just on the heating.
Yeah.
That wasn't putting any value on the cooling that was potentially being provided, which can almost double, not exactly double the COP, but that's effectively what happens when you get to the nirvana. You can consider your COP is just about doubling to 10 or so.
Correct. Yeah, around about 9 or 10 is what we're looking at modelling at the moment. Yeah.
Wow. And from what we're seeing, that heat pumps are certainly viable at COPs much lower than that. 5 looks like a no-brainer. If you've got a low temperature lift, you're only needing 60-degree hot water or so. That's giving you that COP easily a 5, and it looks like that's coming towards a no-brainer at that stage. At 10, it must be just, as you said, nirvana.
Yeah, well, with the hot water systems for swimming pool centres, obviously the majority of the heat is at around about 28 degrees in the pool. That's what you're heating the pool to. But of course, you heat your spas to hotter than that, maybe 30, 32 or something like that. So you need a hotter water because you can't use the pool water because of you've got to heat that with another circuit of hot water. So we try and limit the temperatures as much as we can, but where we're getting COPs average, because obviously it differs throughout the year, average of around somewhere between 5.5 and 6.
Perfect. And maybe that leads us back then into Doyle. You had a spreadsheet to share. I mean, I think if we close it in say 6 minutes time, I think we've got time then to have a quick look at that data. It's always good to see the hard numbers there. Maybe you'd like to come off mute and share that one and just take us through that, how you guys were measuring those benefits and things. Yep, that's coming through. Doyle.
See that there? So this is basically we have a weekly sort of spreadsheet that gets sent out to each of our plants, and we monitor our utility performance, electricity, fuel, and water use. So basically, what we've got here is sort of 4 graphs. The bottom 2 are looking at our fuel use, so our diesel use on site. So the blue line represents our diesel use last year. So it's done per unit of production, so gigajoules per unit of production. So the left bottom graph there is looking at our week by week fuel use, so diesel use. the blue line comparing to the green line for the same week the year before. So you can see there's a bit of separation between the blue and the green line week to week. And then on the right hand boiler fuel use chart there, graph shows a year to date fuel use per unit of production. And what they're showing there, compared to the same time last year, we've got about a 60% reduction in diesel use per unit of production. And then above that, we've got how our electricity use has changed over the same time period. So again, on the left-hand side, just showing our weekly electricity use per unit of production. And then and on the right hand side, our year-to-date electricity use per unit of production compared to last year. So I guess we've been able to achieve, I guess, quite significant benefits in fuel savings. So like I said, 60%, but sort of perhaps a little bit surprisingly, our electricity use has remained about the same, or perhaps even improved by about 5 or 10% with the installation of this heat pump. So I guess so what that means is basically the plant's getting green smiley faces for how they're tracking against their year-end targets for electricity and fuel use. And the trend arrow, the red arrows, that's just comparing week to week sort of thing. So yeah, it's performed really well for us, and it's delivering the paybacks that we were hoping that it would. So, yeah.
And I think you mentioned, is it 2 or 3 years payback there? Is that
Yes.
some government subsidy, or that was just on was that the whole cost?
Yeah. So if we looked at that's with the government. Sorry, if you excluded the government subsidy, we'd be looking at about a 4-year payback, but with the government subsidy at half that, so about 2 years. But we've done a bit of work on some of our other plants. We were needing to replace existing coal-fired boilers, and we're looking at heat pump options, high temperature heat pump options for them in combination with biomass boilers. And yeah, they certainly stack up pretty well against biomass, most other forms of heat energy. So it's something that we'll look to try and roll out across some of our other plants as time goes on, and there's a need to replace boilers, yeah, or provide extra energy production at our sites.
I know there's lots of requests for case stories and things, and I think we'd love to help you get a case story out there and get this sort of data more widespread. So we'll like to keep in contact with you, Doyle. This is a great story here. Just in the sort of final minute before I say thanks to all the panelists and teams, Brian, any couple of words, if you were going to do this again, what would you do differently?
Not sure. Just more time to install it. Yeah. No, we were reasonably fortunate. We had some good, good people around me. Grant here, he and his team, they were onto it, and it was a pretty exciting installation for them. It was kind of very new, and so they wanted to be part of it. So that was always going to be a positive for us as well. Mm. And as Doyle said, we had our group engineering manager. He was sort of driving it. So when everyone's sort of pulling in the same direction, that always has a positive outcome. So no, we're nothing. There was no real major catastrophes that I could sort of share.
Good to hear. Well, we look forward to getting more details and making a case story. And congratulations on a great project. And only that hope to see more of these to come. In terms of energy productivity, it's just a great step forward. And people need this confidence and experience and sharing from you today to help them move on these projects. So thank you so much for that, Doyle, Brian, and Grant. Mike, thanks for joining us, as well as Tony, and of course to Cordin. Thank you so much for that presentation today. I suggest that will be seen as something of a heat pump Bible around here for the next few years. So we really appreciate it. It's been great to hear what's happening. There's a lot of progress since I've seen your presentation done on this in about 3 years ago. So there's a lot happening in this market and a lot of progress. So thank you so much for sharing that with us today. And thank you to all the panelists. Thank you for our attendees for joining in, participants. Great to have you there. As I mentioned before, this presentation has been recorded and we'll send that out next week along with the slides. And yeah, we look forward to joining you, if you can join us at our next A2EP event, being the Energy Users Network meeting, where we can get more into government grants and energy pricing trends as well. But for now, that will do us for A2EP. Wish you all a very good evening, and to Cordin a very nice day. And thank you all, and see you again hopefully in a couple of weeks.